I got a call from my big four-star general boss who said President Obama was going to come down to the Cape and announce a commercial space initiative.
You were previously the Vice President of SpaceX Mission and Operation Launch System. What inspired you to work at SpaceX?
It was just me and this guy, Elon. Not long after that very impactful meeting on my life, I decided to put in my retirement papers from the U.S. Air Force, and then I was fortunate enough to get selected to be the site director at the Vandenberg launch site for SpaceX.
How did you engineer a system that could adapt to such diverse mission requirements?
Yeah, it was very...
Alright, so about 25% of you guys that watch our video say they've not so even subscribed. So if you are watching this video, please do that. This is a little way of showing our support to supporting the team, people who are editing the videos, who are working here with us to make things possible. We built a community like probably the biggest tech community in Africa, connecting CEOs, top CEOs, best engineers from around the world. So we're doing our best to make sure we provide quality content. So, but you can only push us forward by just subscribing to the channel, and that will mean a lot to us. Thank you. All right. Good day, Mr. Lee. It's a very good pleasure to have you on this podcast, Josh Podcast. A lot of people see you today as the co-founder and CEO of ThinkOrbital, and also you were previously the Vice President of SpaceX Mission and Operation Launch System. And we'd like to talk about the project you've worked on doing your moment with SpaceX, and also what you guys are building at ThinkOrbital. So it's truly an honor to have you on this podcast, sir. Thank you.
Thank you very much for having me. I also had a career before those two things as well in the United States Air Force as an engineer, acquisition officer, and space operator. So if we want to take a dive there, I'm very happy to.
Definitely, we are definitely going to take a dive through that as well. So all right. So I reached out on your LinkedIn, and I'm a very big fan of rocketry and robotics. So, and I built this podcast so that everybody could learn from people like you. So can you walk us through your journey, even before SpaceX and after SpaceX, right? And maybe if based on the question I want to ask you, probably there's some few things that must have prompted you why you worked at SpaceX. So at SpaceX, you were deeply involved in building launch infrastructure, right? So what were the toughest engineering and operational hurdles in scaling from early Falcon 1 to the hundreds of regular Falcon 9 launches? So, and before you get there, before mentioning these toughest engineering hurdle that must have been encountered back then, you can also walk us through what inspired you to work at SpaceX despite how massive the engineering could be and how tough it can be. Yeah.
I started my journey as a young person, very interested in mechanical things. I was one of those kids that would take apart my parents' lawnmower and try to reassemble it, or I was a bicycle mechanic as a youngster, and was into things like ski bindings and putting things together. And my earliest jobs were all of that. But decided that, like my father served in the U.S. Army Air Corps, I wanted to serve in the United States Air Force and be a pilot. So I went to the United States Air Force Academy in Colorado Springs, where I majored in engineering there, and had a wonderful 23-year career in the United States Air Force, again as an engineer, acquisition officer, and space operator. Did multiple assignments at the Space Systems Command, where the U.S. Space Force now buys all of its space hardware. Did more assignments at the National Reconnaissance Office, the folks that buy and fly the United States fleet of spy satellites. And then also had the opportunity to command at both of the launch bases, at both Vandenberg Space Force Base and at Cape Canaveral Air Force Base. And while I was at Cape Canaveral, I got a call from my big four-star general boss who said President Obama was going to come down to the Cape and announce a commercial space initiative that we were going to be launching cargo and humans on commercial vehicles to the International Space Station. This is back in 2010, so a long time ago. My boss said we should tour the president around, and I'd like you to conduct the tour. I said I'd be honored to do that, of course. And he said, well, where should we take the president? I said, well, we should take him over to the new Atlas launch pad. It's beautiful. We had just built it. It was ready to go for the Atlas V rocket. And he's like, well, let's take him to one of those new launch pads for that little company that you helped get going here on Cape Canaveral at SpaceX. And I said, oh, sir, I don't know if that's a good idea to take the president to the SpaceX pad. Something will blow up or the president might fall in a hole, and that would be very career limiting for both of us. But the decision got made. We went to the SpaceX launch pad, and while we were waiting for President Obama to come, it was just me and this guy, Elon, hanging out in this hangar that had just been put up for the occasion. There was a fake rocket on the pad as well. And while we were there, Elon kept quizzing me about, what do you do with the rocket after you launch it? Well, it becomes, goes in the ocean and that's it. He's like, do you know any other mode of transportation that you throw away after you use it once? And I said, no, I can't think of one. He's like, well, how would you land a rocket? And I said, you mean like landing the space shuttle? He's like, no, very different. I'm like, well, you could put aero surfaces on it. You could use parachutes. You could do a whole bunch of different things. It's like, oh no, that's too heavy and parachutes won't work on Mars. And I'm like, wow, this guy is a little bit crazy, but he has something here. And at that time, all of the US's launch capability from a commercial perspective had pretty much been offshored to both Russia and to France. And the US launch industry was not doing, maybe one or two commercial launches a year. And on the military side of the house, both Boeing and Lockheed Martin had combined into a single entity. So there was no more competition, even in military space launch in the US. And in my mind, I felt like we needed to have some type of competition here in the US. And Elon was really the only alternative at that point. And not long after that very impactful meeting on my life, I decided to put in my retirement papers from the U.S. Air Force. And then I was fortunate enough to get selected to be the site director at the Vandenberg launch site for SpaceX. And we had the task of taking down a Titan 4 and a Titan 2 launch pad at Vandenberg, which I had worked on as a young captain in the United States Air Force, launching Titans, back in the day. And it was a monumental task. Elon was very much involved in making sure that we got it done very quickly and in a very short period of time. And for a relatively small amount of money, we were able to transform that launch pad from Titan 4 to Falcon 9 and Falcon Heavy. It took us about 18 months or so to do it. And, got to experience that first launch of Falcon 9 there, did a couple more Falcon 9 launches there. And then Elon asked me to come down and run launch operations for the company for a number of years. We took on integrating both military, commercial, and civil payloads on board Falcon 9 and Falcon Heavy, and then flying the Dragon spacecraft, both the cargo and the crew version. So SpaceX was an absolutely amazing opportunity. And I'm sorry this is taking so long. I'm pretty old, so
No, so
get through the curriculum.
no, actually, it was a wonderful story. Yeah, please go on, continue.
Yeah. And while I was at SpaceX, I had this entrepreneurial itch that I wanted to scratch. And we had always talked about the different constraints of outer space while we were there. And I think we did a pretty good job at SpaceX of overcoming the constraint of getting to outer space, right? Because now launch is reliable, it's affordable, it's very high cadence, all the things we had kind of always dreamed of. And they're continuing that tradition. My biggest year of SpaceX was 30 launches. This year, they're going to hit close to 200 launches. It's amazing how they continued to go even better and faster than we were able to do it. And then, this call is coming to you over Starlink. So, for around $100 per month, you can have data pretty much anywhere on the planet. That's another constraint that is eliminated essentially. And in my estimation, the next big constraint that we have to go after is the size of things in outer space, because everything in space is very small compared to any terrestrial application, right? You wouldn't build a factory on Earth that's 30 meters long and 5 meters wide, right? Because you can't scale. And that's what we're missing in outer space is the ability to scale. The biggest structure in space is the International Space Station. That's about 1,000 cubic meters. That's relatively small. So we came up with this great idea, my co-founder, Dr. Voida Holub and I, of building huge infrastructure in outer space. And he had a great idea for basically taking a football, made up of pentagons and hexagons, stacking that flat, and then reassembling that football in orbit, and using precision robotics and some welding and things like that to have a rigid structure. So we had to even go invent the tools for doing that. And the tools that we settled on for that is a technique called electron beam welding. And basically, an electron beam welder has been around since the 1960s. It's used extensively in the nuclear industry. We used it at SpaceX to weld the thrust chambers of the engines together. So it's a fairly well-known science, but the electron beam welders themselves are about the size of your desk, and are very heavy and very cumbersome. So we were able to invent a small, lightweight, lower power electron beam welder with partners in the UK to be able to weld up, aluminum of various, up to about half-inch aluminum or so. And you can see some of the welds that we do here in our vacuum chambers here in Colorado. So it's very interesting form of welding, in that it has to be done inside of a vacuum chamber. And we all know where there's a great vacuum chamber, and that's in outer space. So we did a lot of work on electron beam welding, and we're still doing that work on electron beam welding. We're taking our electron beam welder and a robotic arm with a partner company called Lodestar in the United Kingdom, and taking that down and demonstrating in vacuum electron beam welding for NASA just later this month. So that's super exciting. The other thing we're going to be doing for NASA is demonstrating electron beam cutting, and the cutting is very interesting as well. So here's an example of electron beam cutting. This was a flat piece of aluminum before, and then basically what you do is electronically steer your electron beam back and forth and are sculpting metal from side to side. So a lot of applications for electron beam cutting as well. And one of the other interesting effects of electron beam is that if you take those electrons that are moving about 1/10 the speed of light as they exit that electron beam welder and slow them down very quickly, they emit radiation, and that radiation happens to come in the form of X-rays. So we did a bunch of experimentation with X-raying our welds, and not only could we see through the welds, we could see beyond the welds and into the vacuum chamber, which was very interesting. And then my kind of military background kicked in and said, wow, if I could actually see inside something in outer space, I would be able to tell what it's made up of, what its components are, what its characteristics might be, if it's hiding anything inside, things like that, which is a very useful tool for a mission area called space domain awareness. So the ability to kind of know what your adversaries are up to in outer space is absolutely critical. So that's kind of how we've evolved the company to focus on this X-ray type of capabilities, not only the welding, cutting, and assembly piece, which is still the long-term vision, but in the near term, focusing on this electron beam-based X-ray system. And it turns out the math and the physics closed to be able to do this at some quite far distances, over 10 kilometers, to be able to resolve images inside somebody else's satellites. And it can be helpful for your satellites as well, for anomaly resolution and things like that. So that's kind of the backstory and the history. A long time. I apologize for taking so long.
Yeah, thank you so much. It was very insightful. I really appreciate that. So running, you talk about running mission operation across military, civil, and commercial flight, right? Meant for balancing very different priorities. So how did you engineer a system that could adapt to such, diverse mission requirements?
Yeah, it was very interesting discussions we had with all of the customers. I think, the commercial folks were just happy to get a ride into outer space that was affordable. So they were more after the reliability and the safety piece. NASA, of course, and the Space Force and Air Force had a very different priority. They wanted a certified system to be able to get them into outer space. The certification process for not just the human space flight, of course, but for all space flight for NASA and for the Space Force was very extensive, from ground systems through launch vehicle systems and things like that. So we worked through that with them. It took a long period of time. We started launching Falcon 9s in 20, I think the first one was 2010, or mid 2010, and our first GPS launch wasn't, for 5 or 6 years later. So it took them a long time to get comfortable, at least the military, with actually launching on board Falcon 9. It seems like it's so routine today, but it really took a long time to get them comfortable with what we're doing. So that diverse customer base was something that we worked very hard on to have individual teams that focused on that. The human spaceflight piece was a whole different ball of wax, because now you had Dragon involved as well, and even on Cargo Dragon, the first time you approach the International Space Station with a visiting vehicle, we were the first commercial vehicle to visit the International Space Station. Just the certifications there alone, the amount of simulation analysis and things like that took a long period of time to get there. And then, of course, the human spaceflight piece, there was a extensive amount of negotiations with NASA on the human spaceflight piece. Everything from the suits to the seats to the reliability of different components on the vehicle and things like that. It was a long and arduous uh, negotiation process, and I'm so grateful to one of there was a team of folks that were doing it, but we were very fortunate to have a former NASA astronaut on our team, Garrett Reisman, who's a dear friend of mine to this day, who bore the brunt of poke at SpaceX saying you're not pushing NASA hard enough, and bore the brunt of NASA saying you're not you're not pushing SpaceX hard enough for us, and kind of was that guy in the middle that was the punching bag.
Yeah.
And Garrett did a masterful job of getting both sides to agree to all of the most important things. I think a great example of that is every vehicle that most folks in the military and at NASA fly has handles to pull for ejection, right? Or a stick that you fly with, right? And SpaceX proposal was, we don't want a stick that you fly with. We want to fly all on touchscreen, and we don't want a handle for abort. The abort should all be automated, and if they need to initiate an abort, it will be on the screen, and they can do that, right? So we went through an extensive amount of testing with human subjects and things like that to decide which type of flying was better, stick flying or flying with the touchscreens. And it turns out, from a human factors perspective, the touchscreen flying was actually better than the stick flying. NASA would not relent on the handle for the abort. So if you notice in the center of the Dragon console, there's kind of a T handle that you pull and rotate out if the astronauts need to. So there was compromise on both sides, and I think that was a good example of the stick and the abort handle.
So you talk about the Dragon mission. So the Dragon mission had the major leaps, right? So what were the key challenges in designing and running crew and cargo operation that meets NASA strict safety standard?
Yeah, I think on the design side of the house, there were just so many different components to both the cargo and the crew version of Dragon, right? So many different systems, from the had abort system or the abort system, which took a while to get certified. For a while, we were trying to land the capsule on ground, not in the ocean. And at some point, we had to say, okay, we're going to not do that just because getting it certified would take too long.
Yeah.
So that's why the parachutes kind of evolved. The parachute system took forever to get certified. There was all kinds of issues with parachutes. You'd think that that would be a fairly well-known science, but it's really not. And there was a lot of experimentation with the parachute system. Even the bathroom system had a lot of different issues that had to get worked through, and there were some minor issues that happened with the bathroom system on a couple of different flights and things like that.
Yeah.
So I think it's just it was you know at SpaceX, systems engineering is an interesting word. There's really not a dedicated systems engineering group at SpaceX. It's more every group is responsible for its own systems engineering and to interface with the other groups. And this was a huge systems engineering challenge because you had so many different subsystems that you had to account for, and you had to convince NASA that each one of these subsystems was reliable. And we did a lot of testing. And I think that's one of the great philosophies that Elon always brought to the table was that every problem that you're going to have in outer space is apparent on the ground. It's there. All you have to do is go find it. And the philosophy was we're going to test it so hard and to the point where the system will break on the ground, but that's okay because we'll know where the weak points are and can find out where those flaws are on the ground versus finding them when it's too late and you're in outer space and there's not much you can do about it.
Yeah. Yep, you said something about every team have their own design system they should work on. So definitely, I know about that. I have some friends who work at SpaceX. So talking about astronaut training, yeah, definitely we know that their training is at high stake. I mean, so what innovation did you and your team bring to the Dragon training, both rigorous and efficient compared to the traditional program?
Yeah, I think the fact that we had astronauts from very differing backgrounds. Yeah, we had our first mission with Colonel Bob Behnken and Colonel Doug Hurley flying that first mission. These were professional astronauts that had flown several missions before. Their level of training, when they got to us was at a very, very high level, right? Those guys were super pros, and all of the NASA professionally trained astronauts were, that they had that flight and space flight awareness about them, which is something that takes time to really train in, and they do an amazing job of that at NASA. It was definitely more challenging when you had uh, like folks that flew on the Inspiration 4 mission that Jared Isaacman kind of was the captain of. And Jared is a great airman. He knew, was is a brilliant guy. He had studied up, but the entire crew, many of those folks had never flown in space before. Some of them weren't engineers, and the baseline from where you started was very different than a Colonel Bob Behnken and a Colonel Doug Hurley, which was these guys were up here, and they're all smart people. So it was really trying to get everyone up to that same level of understanding and coming up with a baseline that was difficult, and getting them to really dig in and understand the systems, right? And if you're not an engineer or you're a medical professional or something like that, it's not something that's in your normal day to day. So they did, and to a person, everyone that we trained just worked incredibly hard with our amazing trainers who had the information available to them. All of the engineering teams were available to them to ask questions and things like that. So SpaceX did an amazing job of the training piece of this as well. Even though it was a relatively short training cycle, it was a very, very intense training cycle.
Yeah, I understand the fact that it takes a lot of time for people to get trained before they go to space because we understand how dangerous it is. So, last question on space before we dive into ThinkOrbital, right? So, this is the most powerful question, I believe. So, looking back then, which of the single engineering decision or design psychology as pieces did you make that like did you make the biggest long-term impact on the mission reliability? Yeah.
Yeah, I'll never forget sitting in a meeting with a group of very well-informed NASA people, and then saying that there's no way that you will be able to do a propulsive landing of a rocket because supersonic retro propulsion is just not possible with the technology that we have today. And basically, supersonic retro propulsion means the ability to basically relight the engines as you're coming through the firestorm of the upper atmosphere to be able to slow that vehicle down enough and do that. And uh, you know, the design philosophy that led to that was the only law that you can't break is physics, right? And there's a lot of people that, you know, have rules and regulations and over constrained problems. But the design philosophy at SpaceX was if you're not violating a law of physics, it is possible. So let's go figure out how to solve the hard physics problem. And then we'll worry about the other stuff, the rules, the regulations, the system norms, and things like that. And I think that's a very, very powerful design philosophy that we use here as well.
Yeah, and I also remember the first principle regarding spirit. Elon mentioned that a lot on his interviews. Thank you so much for the input, right? So now getting back to Think Orbiter, you talk about wedding system, X-ray, imaginary or stuff like that. So Think Orbiter just launched the world first autonomous in-space wedding system based on what I saw on your website. So can you walk us through the engineering breakdown that made you wade in a microgravity in a microgravity possible?
Yeah. So the welding piece, is fundamental to being able to build big things in situ, right? If you want to have that scale, if you want to have that size, you have to build where you need it, right? You wouldn't build the Empire State Building uh, in New Jersey, put it on a truck, and take it to New York City, right? Big things have to be built where you need them. And I think the same rule really applies for outer space. And we've been doing it the same way for 70 plus years, right? We build the biggest thing possible that can fit on the biggest rocket possible, cram it inside that rocket, and launch it into outer space. Yet everything is still relatively small, as we mentioned before. So I think, figuring out what that principal way of building in space was really important. And, we know the advanced state of precision robotics today, so that part wasn't hard. But the welding piece is something that really hadn't been demonstrated fully in outer space. There were some experiments done by the Soviets back in the 80s. There was some electron beam welding that was done on Skylab, inside of Skylab. But we don't really have great knowledge of those results. And it was kind of an afterthought. And we felt it very important to be a real space company. You have to have spaceflight heritage. So we figured out a way to get spaceflight heritage relatively quickly by watching our welding capability and getting samples back that were phenomenal. And both NASA and the European Space Agency learned a tremendous amount about microgravity welding. The grain structure looks different. The depth of the weld pool looks different. The heating and the cooling zones look different than the same samples that we did here on the ground for them. So it was very informative for them. So we contributed to science, and we proved that we knew how to build things that could work reliably in outer space. So it was a really a great win. the pivot to the X-ray piece really happened when unfortunately, I'm not sure the world is quite ready for building huge infrastructure in outer space. And as a startup company, the first rule is survival. So we had to pivot to an area that has shown some great government traction, and the X-ray piece really is that pivot to really keep the company alive and do something that we feel is really important for our nation.
Thank you so much for that of the uh, answer you gave. I'm a big fan of Soviet Union. On my LinkedIn, Instagram, I post a lot of the wonderful tech, right? So I believe maybe you know some of this knowledge that has been some of the experiment that has been tested out years and years ago and still worked on today and years to come, right? Whatever thing that has been learned, I mean, is going to help the future startups or technological enterprise to make such infrastructure possible in space. So, talking about the Think platform, right? Think Orbiter. So, Think platform promises autonomous in-orbit assemblies. How do you approach designing a system that can handle the unpredictability of space construction without human intervention?
Right. So yeah, the Think platform will be a revolutionary type of platform because it will really be the first thing ever built in outer space, right? The International Space Station and the Chinese space station were kind of assembled in outer space, and they were kind of prefabricated on the ground, right, and then assembled in outer space. But really, nothing has been manufactured in outer space from anything of a major volume. So the ability to actually do that, we think, is just fundamental to humanity's future in space and to a new space economy that includes things like manufacturing, large scale human habitation, military missions, and forward basing, and things like that. So those kind of things are enabled by some really basic technologies, and we mentioned some of them before, but the ability to use precision robotics to assemble these pentagons and hexagons of your football together is not a new science, right? It's something that we've got fairly well understood today. By mechanically latching them together and giving it a little bit of time to thermally stabilize, now I don't have to worry about welds not lining up and peeling out. The electron beam welding, the fact that we've been working on this for a while now and really understand how the electron beam behaves in outer space, gives us a good launching pad to be able to um, really make an airtight and rigid structure in outer space of theoretically unlimited size. And in fact, we won a contract with NASA to talk about building an O'Neill cylinder sized structure in outer space, basically a dry dock like you would build a ship in outer space. They have this NASA innovation contracts that they hand out for folks with wacky ideas, and our wacky idea was build a dry dock to build those big ships in outer space. And so it is a little bit ostentatious to think that you could do this, but again, we're not violating the laws of physics. We think the technology exists today to be able to do this type of assembly, and it's just a matter of finding the right customer that can fund essentially building one of these large structures. Now, you've got a big empty structure in space, and by our calculations, if we launched all of the material on a single starship, we could build 4 times the volume of the International Space Station on a single launch. That's 4,000 cubic meters is a lot of space and way bigger, obviously, than anything in outer space. So you've got a big empty volume. Now, what do you do with it, right? Well, you have to bring up other vehicles to it to outfit whatever manufacturing you wanted, whatever human habitation. If you wanted to build a hotel or a sports stadium or a research facility, you'd have to bring all that other stuff up. But really, the fundamental piece here is that real estate in outer space, and having a place to do that, I think, is really the important piece.
Thank you so much for that. I really appreciate the answer to that. It was very valid. Um, last but not the least, the last question but not the least, before so that we can end this first section. So you already secured contract and demos to prove the tech, right? So what are the kind of the biggest validation milestone you are targeting over the next few years from now?
Yeah. So again, this test that we have of the in-space construction piece down at NASA over the next month and a half or so is really validation of the welding married to the robotics piece of this. So I think we have an important series of tests coming up that will validate that. On the X-ray side of the house, uh, we are building a long vacuum chamber here at our facility in Colorado. It's over 10 meters long, and this will give us the insight to make sure that the math that we've been doing to show that we can do this X-ray imaging at over 10 kilometers will work out. I wish I could build a 10-kilometer long vacuum chamber, not super practical for a small company or anyone really. The ability to actually test this thing terrestrially is very exciting. And then just last month, we announced that we are launching into outer space uh, twice next year with our good friends and host satellite called Argo Space out of El Segundo, California. Three SpaceX brothers, literally, they're all three brothers that work at SpaceX, have this great, super highly maneuverable spacecraft that is capable of rendezvous and proximity operations. Those two launches that we're doing, one will have our detector on it, one will have our X-ray source on it. We'll meet in geostationary orbit this time next year, and we will shoot X-rays from one satellite to the other satellite. Hopefully, I'll get an image of something in between. I'm working.
Definitely. I'm also looking forward to that. Probably, if that can happen in a few years from now or sooner, I would like to discuss about that on our next podcast, right? So while we are ending this section, so we can talk about fully about this S3 on another section. So I really appreciate your time for talking about SpaceX and see about ThinkOrbital, right? Thank you so much for this first section, Mr. Lee.
My pleasure. Thank you so much. I really enjoyed it.